Hello everyone, welcome to this lecture. So, in this lecture we will continue our discussion regarding bivariate polynomials over a finite field. In the last lecture we had proved the privacy lemma. In this lecture we will prove another important lemma, namely the pairwise consistency lemma, and this also will be later useful when we design verifiable secret sharing schemes based on bivariate polynomials. Okay, so, what exactly is a pairwise consistency lemma statement? So, again our setting is the same. We have a finite field, we are given n distinct non-zero evaluation points alpha 1 to alpha n, and you are given a subset of n indices k, where the size of k is at least t plus 1. So, you are focusing on a subset of at least t plus 1 or more number of indices, and you are given pairwise consistent t degree polynomials corresponding to those indices. So, you are given x univariate polynomials and y univariate polynomials corresponding to the indices in k, the set fancy k, and they are given to be pairwise consistent. What does that mean? That means that if you focus on any pair of indices I j in this subset fancy k, then the x univariate polynomial evaluated at alpha j gives you the same value as the jth y univariate polynomial evaluated at alpha I. Okay. If this is the case, then the claim is the following. The claim is that there exists a unique t degree bivariate polynomial over the field, which would have resulted in the following: when that bivariate polynomial evaluated at y equal to alpha k would have given you the kth x univariate polynomial, and the same bivariate polynomial when evaluated at x equal to alpha k would have resulted in the kth y univariate polynomial for every index small k in this fancy k. What does that mean? So, on a very high level what we are trying to say here is the following. We know that for the case of univariate polynomials, if I give you t plus 1 distinct points, any t plus 1 arbitrary points, pair of points who are distinct. So, which are distinct, namely their x components are distinct, then I can always pass a unique t degree univariate polynomial through those t plus 1 points. Now, we are trying to generalize it for the bivariate polynomials. So, always remember that in the context of bivariate polynomials, the points can be treated as the x univariate polynomials or the y univariate polynomials. So, you are given t plus 1 or more number of pairs of x and y univariate polynomials, which are guaranteed to be pairwise consistent among themselves. That is important. Even though they are t plus 1 pairs of arbitrary univariate polynomials, they have to be pairwise consistent, then only this uniqueness property will hold. Okay. So, if they are pairwise consistent, then basically what we are arguing here is that there exists a unique t degree bivariate polynomial passing through those t plus 1 or more number of pairwise consistent univariate polynomials. You can't have multiple bivariate polynomials passing through those given t plus 1 or more number of pairwise consistent polynomials. That is the statement here. Okay. So, we will prove this and then later we will demonstrate it. So, you are given t plus 1 or more number of pairwise consistent x and y univariate polynomials, right. So, focus first on any t plus 1 of them. So, remember the number of pairwise consistent bivariate polynomials could be more than t plus 1. If it is more than t plus 1, focus on any t plus 1 of them, any t plus 1 pairs of those pairwise consistent x and y univariate polynomials. So, the indices corresponding to those t plus 1 univariate polynomials I am denoting as fancy L, and again without loss of generality and for simplicity assume that those t plus 1 pairwise consistent x and y univariate polynomials correspond to the first t plus 1 indices. Now, first what we will do is the following. We will show that if you are given the pairwise consistent f 1 x up to f sub t plus 1 x and g sub 1 y up to g sub t plus 1 y, and if they are pairwise consistent, then through this t plus 1 pairwise consistent x and y univariate polynomials, I can always pass a unique t degree bivariate polynomial. This is what first we will prove. So, first what we will do is we will take the x univariate polynomials, the t plus 1 x univariate polynomials, and apply the Lagrange interpolation for the bivariate polynomial and get a unique t degree bivariate polynomial passing through those t plus 1 x univariate polynomials. We have not yet touched the t plus 1 y univariate polynomials. We have just touched the polynomials f sub 1 x, f sub 2 x, f sub t plus 1 x, and through them we have interpolated a t degree bivariate polynomial f of x y. What we will end up eventually showing is that all other remaining polynomials which are given here in this system, which are pairwise consistent etc., also will be lying on this bivariate polynomial f of x y. But right now we have just used the first t plus 1 given x univariate polynomials to fit a t degree bivariate polynomial f of x y. So, this is what pictorially we have done. Okay. Now, what you are given? You are given that if I take any y univariate polynomial g k y, where k is one of the indices in this fancy set k, right, then it is pairwise consistent with the first t plus 1 univariate x polynomials. Okay. Why first t plus 1? Because I am assuming for simplicity that the set fancy L consists of the first t plus 1 indices. That means, if I consider this polynomial g k y, then because of the pairwise consistency fact, we have this equality, namely the kth y univariate polynomial when evaluated at alpha 1 is same as the first x univariate polynomial evaluated at alpha k. I am just triggering the pairwise consistency condition. It is also given that the same kth y univariate polynomial evaluated at alpha 2 will give you the same value as the second x univariate polynomial. Okay. So, this kth y univariate polynomial at alpha 2 and the second x univariate polynomial at alpha k have the they are the same values, right. And like that, the kth y univariate polynomial at the t plus 1th evaluation point is given to give you the same, it is given that it give you the same, its value is same as the t plus 1th x univariate polynomial evaluated at the kth evaluation point. Now, we also know that this first x univariate polynomial is nothing but the first row polynomial on my bivariate polynomial which I have interpolated. So, if I evaluate this f 1 x polynomial at alpha k, then that is nothing but this particular point on my bivariate polynomial. In the same way, I have interpolated my bivariate polynomial f of x y using f 2 x. So, f 2 x is nothing but the second row polynomial on my bivariate polynomial, and because of that this point f 2 of alpha k is nothing but this particular point on my bivariate polynomial. And like that, my t plus 1th x polynomial also lie on my bivariate polynomial. It is specifically the t plus 1th row polynomial, and that row polynomial evaluated at alpha k is nothing but this specific point on my bivariate polynomial. Now, what I have shown here? I have shown that there are t plus 1 points on my bivariate polynomial, which are this highlighted point here in the kth column of my matrix. These are the t plus 1 highlighted points in the matrix. They also lie on my gky polynomial. And what is the degree of gky polynomial? The degree of gky polynomial is nothing but t degree. It is a t degree univariate polynomial. And what are these highlighted points? These highlighted points are nothing but points on another t degree univariate polynomial in Y, namely the kth column polynomial of my bivariate polynomial f of x y. That means, what I have shown here is the kth y univariate polynomial which is given to me and the kth column polynomial of the interpolated bivariate polynomial, they have t plus 1 common points and their degrees are t. So, we know that if two t degree polynomials have t plus 1 or more number of common points, then they are the same polynomials. So, we have two different univariate polynomials here, the gky univariate polynomial which is given to us and the kth univariate polynomial, namely the kth column polynomial also in Y, whose degree is also t, and there are t plus 1 points, namely the highlighted points here, which lie on the kth column polynomial of the bivariate as well as on the gky polynomial. Then it automatically implies that kth y univariate polynomial which was given to me is nothing but the kth column polynomial lying on the interpolated bivariate. And here k is any index from my set fancy k. That automatically shows that whatever I have argued for gky holds for g1 of y, g2 of y, g of t plus 1 and so on. That means, what I have shown here now is that all the g polynomials which are given to me. So, I was given t plus 1 or more number of pairwise consistent x and y univariate polynomials. I have used the first t plus 1 x univariate polynomials, interpolated the bivariate, and now I have shown that all the y univariate polynomials, not just the first t plus 1, all the y univariate polynomials, they also lie on that interpolated bivariate polynomials. Now, what is left? It is left to show that all the remaining x univariate polynomials, remaining means which were there in the set whose indices are in the set fancy k, but not in the index set fancy L, they also lie on this interpolated bivariate polynomial f of x y. And again, to prove that, we will trigger this pairwise consistency statement. So, consider any x univariate polynomial outside the first t plus 1 x univariate polynomial, different from the first t plus 1 x univariate polynomial. Okay. Now, what we are given, what we know about such x univariate polynomials. So, we are given that this kth x univariate polynomial evaluated at alpha 1 gives you the same value as the first y univariate polynomial evaluated at alpha k, because of this pairwise consistency. In the same way, this kth x univariate polynomial at alpha 2 is given to be same as the second y univariate polynomial evaluated at alpha k, and like that this kth x univariate polynomial evaluated at alpha t plus 1 is given to be same as the t plus 1th y univariate polynomial evaluated at the kth evaluation point. Now, what can I say about g 1 evaluated at alpha k? Well, g 1 evaluated at alpha k is nothing but a point on the bivariate polynomial, namely it is this point f of alpha 1 alpha k. So, that means we have, I can rewrite this equality like this. In the same way, what is g 2 of alpha k? G 2 polynomial evaluated at alpha k is this second point here in this highlighted row, and which is a point on my interpolated bivariate polynomial f of x y. That means, I can rewrite this equality as this. And in the same way, if I take the t plus 1th y univariate polynomial and evaluate it at alpha k, then that will give me this highlighted point. That means, now I can rewrite this equation, this equality as this, right. Now, what is the degree of f k x polynomial? It is a t degree polynomial, and these points, these highlighted points here, actually lie on a t degree polynomial, t degree univariate polynomial in x. That polynomial is f of x of alpha k, namely they are the points on the supposedly kth row polynomial of this bivariate. Its degree is also t. So, f k of x is a t degree polynomial, and the supposedly kth row polynomial of the bivariate polynomial is also have its degree is also t. And we have shown that the kth x univariate polynomial, it has t plus 1 points, which also lie on the kth row polynomial of my interpolated bivariate polynomial. So, again we can use the fact that if you have two t degree polynomials with t plus 1 common points, then basically both the polynomials are the same. That means, this kth x univariate polynomial is nothing but the kth row polynomial of my bivariate polynomial, and this k could be any k different from the first t plus 1 x univariate polynomials and lying or belonging to the set of pairwise consistent x univariate polynomials. So, you were given many pairwise consistent x univariate polynomials, maybe more than t plus 1. You have utilized the first t plus 1 to interpolate the bivariate, and now I have shown is that if I use the remaining, if I focus on the remaining pairwise consistent x univariate polynomials, I have shown that well they also lie on this interpolated bivariate polynomial f of x y. So, all in all what we have shown is that all these pairwise consistent x and y univariate polynomials lie on a single bivariate polynomial of degree t. We do not care what exactly is the constant term of that bivariate polynomial. What we have shown is that if they are pairwise consistent and if we have t plus 1, at least t plus 1 such pairs of pairwise consistent univariate polynomials, then they lie on a unique bivariate polynomial. Okay. So, let me demonstrate it. For demonstration, I take n to be 7 and t to be 2, and I will be performing all the operations over this field Z11. And since I need 7 evaluation points, I have chosen my evaluation points to be 2, 4, 5, 7, 8, 9 and 10. So, you can now see that unlike previous examples where all my evaluation points were continuous, that means they were is one of they were the consecutive evaluation points from the field. Now, my evaluation points are not consecutive. So, first evaluation point is not 1, not the element 1, it is the element 2, and then I am not taking 3 as one of my evaluation points, but rather I am taking 4 as my evaluation points. But irrespective of what exactly are my evaluation points, the pairwise consistency lemma always hold. So, these are my 7 evaluation points, and suppose I take a proper subset of these evaluation points, namely I take this subset of size 4 and I give you 4 pairs of x and y univariate polynomials corresponding to these indices. Okay. Now, you can verify that these 4 pairs of x and y univariate polynomials, they are pairwise consistent corresponding to the indices in K. So, I would like to stress when I say they are pairwise consistent, they are supposed to, they can be pairwise consistent only within the indices in the set fancy K. If there is some I j outside the set fancy K, then it is not necessary that the corresponding x and the y univariate polynomials, they are pairwise consistent. That is not necessary. The condition of pairwise consistent, the pairwise consistency is given only for every pair of indices within this set fancy K. So, for instance, in this example, my set fancy K has the indices 1, 3, 6, 7. So, that means when I take the first x polynomial, first means this f1 x, and then if I evaluate it at alpha 1, alpha 3, alpha 6, alpha 7. Why alpha 1, alpha 3, alpha 6, alpha 7? Because I have the indices 1, 3, 6, 7. They should give me the same value as the first y polynomial and the third y polynomial and the sixth y polynomial and the seventh y polynomial evaluated at alpha 1. And indeed, it turns out that this is the case. So, for instance, if I take the first x polynomial, this is my first x polynomial, and if I evaluate it at alpha 3 is 5. That means, this particular polynomial, if I evaluate it at alpha 5, is given to be same as the y univariate polynomial corresponding to the index 3. The y univariate polynomial corresponding to the index 3 is this polynomial, and this polynomial evaluated at the first evaluation point, namely 2. Both these values will turn out to be 3, and we can verify, right. So, I am not going through the calculation here, but you can verify here that f I of alpha j and g j of alpha I will be the same values for every I j pair in the set 1, 3, 6, 7, where my evaluation points are 2, 4, 5, 7, 8, 9 and 10. Now, using, so these are my pairwise consistent, these are my pairwise consistent univariate polynomials, and now we can show that there is a 2 degree bivariate polynomial. So, this is my 2 degree bivariate polynomial whose first row will be f1 of x, the given f1 of x, and whose first column will be the given g1 of y, whose third row will be this f3 of x polynomial, and whose third column will be this g3 of y polynomial, whose sixth row will be this f(c) of x, f(6) of x, f(6x) polynomial, and whose sixth column polynomial is this y univariate polynomial, and whose seventh row polynomial is this x univariate polynomial, and whose seventh column is this y univariate polynomial. You can again verify that, I am not going through the whole calculation. So, what we have shown here is that if I so by the way, I am giving you more than t plus 1 pairs of pairwise consistent polynomials here, right. So, I have given you 4 pairs of pairwise consistent x and y univariate polynomials, then passing through them I can interpolate a unique bivariate polynomial. By the way, I am not saying anything regarding what will be the second and what will be the fourth and what will be the fifth row polynomials of this bivariate polynomials, because we are not given them, we are not given that. We are only given the first, third, sixth and seventh row and column polynomials which are pairwise consistent. So, intuitively what you can imagine here is that your f of x y is an unknown polynomial, and there would have been a matrix of n cross n values on that bivariate polynomial. What I am doing here is I am just focusing on a subset of t plus 1 cross t plus 1 or more points among these n cross n points which are lying on that unknown bivariate polynomial through this pairwise consistent row and column polynomials, and arguing that that also is sufficient to interpolate a unique or define a unique t degree bivariate polynomial. Okay. So, with that I end this lecture. So, for this pairwise consistency lemma I have used this reference. Thank you.